Already heard my loud voice all over the Institute. I'm David Ham, and I'm going to basically talk about programming models. I'm going to talk a bit about why we have those programming models. People who've seen me give not utterly dissimilar talks in the room before will have seen me previously give performance results. I'm going to try to avoid giving performance results today, basically because there's some very big design changes that we made over the summer, which may well invalidate performance results that I have previously given, and we don't have an awful lot of new ones as a result of the massive changes we made over the summer, but we'll explain that. But I don't actually think that the individual performance results of, I have no idea, I'm not touching anything.
It was off, but now it just went back on, it seemed like.
The more interesting, is there a problem? Can you not see the screen, or? Okay. So
you turn the light back on again.
So what I'm really interested in working on at the moment, and what this whole horde of people are working on, are dealing with the issue of how we deal with the current hardware revolution that's going on from the one side, but from the other side, how we overcome the absolutely massive amount of time that we spend recoding the same model, which is a really colossal issue. It's especially a big colossal issue in university science. It's probably a little bit less of an issue in big national centres for reasons that I'll get to. So I think there's some sort of contractual obligation to show this chart in every one of the talks that's related to this issue. This is a piece of work that a guy called Sutter did in 2005, and he put a lot of data on the graph and drew some lines. He then updated it in 2009, basically by putting more data on the graph, but not having to move any of the lines, because in 2005 he was right. So these are the scaling curves over time for a bunch of properties to do with processors. And so the big green line is Moore's law. So the big green line is basically transistor density on silicon. And that doubles roughly every 2 years, and has done since Gordon Moore, who built the nice library across the road, announced it sometime in the 70s, and will probably continue to do so for quite some time. The reason why any of us care about this curve is the dark blue line. So the dark blue line is clock speed. So in about 2004, we got 3 gigahertz chips. Now we have, well, probably not even quite 3 gigahertz chips. And there's actually 2 reasons for this one. There is a minor reason. The minor reason is this one here, which is the performance per clock line. So this line here had to do with the increasing ability of the chip makers to put smarts on chip. And so a conventional processor has an awful lot of its silicon devoted to doing things like out-of-order execution. And out-of-order execution means that you can continue to program the chip as if it's a 1960s computer that executes one instruction after the other. But that's really not what's going on, and it will do a lot of local level discovery of things that it can do out of order and therefore can do before something else is loaded. And there was quite a while when we were getting quite a lot of gain out of that, and that sort of petered out. But
is that done in software or hardware?
And on a conventional chip, that is done in hardware. There's quite a lot of silicon which is doing hardware out of order execution for you. It's one of the reasons why you can do the GPU trick that we're going to get to in a second. But the real one, as I guess we all know and as Beth told us last week, is this line here. So this is the power dissipation line. So if you followed this line up, which is pretty much what would happen if you kept putting the clock speed up, because this is a log-log graph, so it does curve up like that, then you will have noticed that in 2010 we would have got 10 gigahertz chips, and those 10 gigahertz chips would have dissipated something on the order of a kilowatt. So the key reason why you can't buy a 10 gigahertz chip is that thermodynamics is a bugger, and all of the power you put into a chip you have to dissipate as heat, and your chip would melt. You just cannot get enough heat off the chip fast enough. At supercomputer level, of course, there's another reason for that, which is that all that power is expensive. At desktop server level, that's less of an issue. And in fact, current graphics cards are basically limited by how much heat you can get off, because gamers don't care about their power bill. Now, a side effect of that is that people who do care about power bills, which is pretty much everybody in this room, also get what they need out of those systems, because the heat and the electricity bill point in the same direction.
A kilowatt doesn't seem so bad. I mean, that's still a single plug in your...
That's one core, though.
Oh, per core.
So, no, so the reason why you don't have a kilowatt processor in a desktop is because it would melt. It's because you cannot get the power off fast enough. Because you're right, you probably don't care about the fact that you're dissipating a kilowatt from your computer. You do care if you've got a data center, but the reason is because you can't build it. So this is what NVIDIA came up with as a solution. So this is a Fermi, which is no longer the latest NVIDIA card. And we'll show you what's happened in the meantime, because it's quite instructive in a second. So
Can you full screen that so it's bigger?
no.
No.
Because it will cut off the side. So this chip is essentially the same silicon wafer that Intel's got, right? NVIDIA don't have access to a magic different manufacturing technique. They've just made a different decision about what to do with the transistors. So instead of putting on now 8 very clever processors, this chip has 500 really stupid processors on it. And so the reason you can do that is because they're not investing an awful lot of space in things like out-of-order execution and other smarts that make your life easy as a programmer. So the plus side of that is you get lots of flops. The downside of that is you lose the comfort blanket of all that programmer assistance that you had on the other chip. In contrast to the predecessors, these things do have a level 2 cache. That level 2 cache is about 200 cycles away from the processor. So that's not an awful lot of comfort blanket. And actually the main memory on this thing is 400 cycles away. So hitting level 2 cache is pretty much a loss. What they locally look like is one of these things. So these are the actual processors. So each one of these on this particular model, 16 streaming multiprocessor units, as NVIDIA calls them, is one of these things. And each one of these is a very small, very stupid processing unit. It's so stupid, it doesn't even have an instruction scheduler. So the instruction scheduler, the thing that says to it at the lowest level, do this, multiply, add now, lives up here. So what that means is that the 16 of these things, you get 2 banks of 16, the 16 of these things execute the same instruction at the same time. In fact, it's slightly more complicated than that. They do it twice. So what you have to have is a warp of 32 threads. They call them warps. The analogy is with weaving. So these are all the lines doing the same thing. A warp of 32 threads has to do exactly the same instruction at the same time. So for those of you in the room with slightly more grey hair than me, one way of looking at that is vectors are back. Because that does look an awful lot like a vector operation, albeit not as long a vector as the vectors that we had 20 or 30 years ago. These things really are graphics cards, and they have some other stuff on here which looks really nice and turns out to be utterly useless for our purposes. So these things over here are special function units. They're great. They can do a transcendental function in 1 clock. So that's really lovely. To about 4 significant figures. So not so useful if you really care about the answer. Absolutely great if all you want is for your ball to look round, which is what they're actually there for, right? If you're doing graphics, you do an awful lot of sines and coses, and you need to get the answer, you don't really care what it is. We do care.
I just want to interrupt. What about logs? Thinking about
same problem. So you can have a log or an exp in no clocks, but it won't be very accurate.
How accurate do you need your logs to be? How accurate do you need your logs to be?
The old hardware used to do it in a sort of intuitive approach, right? Just do those functions.
Right, and
so you use it as a starting point. That would be a good guess for that iteration.
If someone could write the low-level code to do that, that's possibly true. Although whether or not it's worth doing the transfer is another question, right? So one of the problems on these things is that moving data around is ridiculously expensive.
But if I have understood this correctly, which I may not, some of these things could be changed. So what is happening in those?
If someone could build a transcendental function unit to double precision in one clock, I suspect they probably would have
Or
done
not a transcendental function,
So-
some other operation that could be put in the hardware.
Maybe if we can think of them. I mean, I think.
Right. Well, that's
I mean,
that was
so
my point.
one thing they have done. This thing does double precision at half the rate of single precision, which is a really big step up from the predecessor unit, which did double precision at 1/8 the rate of single precision. And that happened because scientists asked for it, because nobody else cares about double precision. So you also get 32,000 registers, which anyone who's ever done low-level programming on an Intel machine sounds wonderful. It's not actually anywhere near as wonderful as you think, because when you use registers on a conventional threaded system, when you switch from one thread to another, what happens is something called a context switch. And basically the state of the processor is saved, you unload all the registers, and the new thread gets access to all the registers. This does not happen on a GPU. So those 32,000 registers have to be shared amongst all the threads that are on this unit, because each thread owns and completely keeps its own registers. So actually you end up really register poor. You also get, so these things can't see each other's registers. They can all see main memory, but main memory is 400 cycles away, so that's pretty much useless.
You said they can see each other's registers.
They cannot see each other's registers.
But you just before said that the register was shared.
The register file is shared amongst all the threads, but they own their bit of it.
Okay.
You get down here 64K of shared memory, which broadly speaking, these guys can see. One thread block can see it, and it makes sense to launch one thread block on here. That's not very much. And it's not even really 64K. You get a choice about whether it's 48K shared memory that you manage and 16K of level 1 cache, or the result, or the reverse. And 16K of level 1 cache is not very much when you need to have. So you need the bare minimum to have this thing running fully loaded is that there are 64 threads on there. And actually, if you remember that you're going to get I/O blocked for 400 cycles at a time, you need to oversubscribe this thing several times over to get anything close to normal production. So now that I've scared you with that, this is the latest one. This is Kepler. This came out in, if you didn't have an NDA with NVIDIA, you could get these earlier this year. People had them last year. So this thing, it's only got, at this level it looks pretty much the same. There's 15 instead of 16. I do not understand why there's 15. It sounds like a really, really weird number of units, but there are 15 of these units here. There's still level 2 cache. The level 2 cache talks to about the same amount of memory as happened before. The difference...
I think there actually is 16. They turned one of them off.
That may be the case. They also advertise the fact that some models may, some of the lower ranked models may have 13 or 14. So one of the things they actually do with these chips is they have fairly significant hardware failure rates in manufacture. And so basically if you buy the 13 processor version, you've just bought one that went wrong.
Right.
Quality control, it's like the
Right.
cartridge for...
So this is pretty much the same concept as what we had earlier, except now these things have got 4 times as many cores on them. 4 times as many cores, only twice as many registers, and the same 64K down here. And this is very much the direction of travel for all the architectures that are out there, right? Putting more cores on is relatively easy. Putting more memory on is really hard. Getting memory latency down is really, really, really hard and probably almost impossible, right? The reason why, and in fact the clock performance on this has got better in some senses, so I haven't seen an official NVIDIA number for how far away main memory is, but I've seen an unofficial claim from somebody who's looked at them who claims it's 800 cycles. So, and once again, okay, they can do things in response to demand. Nobody likes latency. No application likes latency. If that latency could be lower, NVIDIA would be making cards with lower latency. And then the other thing about these is that these things now schedule 2 independent instructions on 1 clock cycle. That's how one of the reasons they get it through. So they, in principle, execute your kernel twice as fast. But to answer Beth's question, as far as I can work out, unlike on a conventional CPU where that does basically happen, but the processor works it out, here the compiler has to work it out. And the compiler has to issue double machine level instructions to tell these double warp schedulers what they're allowed to do at once, because it's not capable of sorting that out. So that's the shocking horror of these things. The way these things actually work, because this isn't a conventional CPU that doesn't run an operating system, there is nothing controlling processors on that. What you have to do is you have to have a companion CPU which has the smarts, which is running the operating system when you actually execute your program. And then what you do is you launch individual subroutines, which are called kernels in the nomenclature of these hardwares. And so what you do is you say to the kernel, okay, I want you to launch n blocks of n kernels, where that should result, hopefully, if you have enough parallelism, in, on one of those things, at least tens of thousands of threads going off. And then they go away. That's a non-blocking operation, so if you can think of something for your CPU to do in the meantime, such as the MPI communication maybe, then you can do that. And then you eventually, they complete, and you either check that they've completed, or at some point you may have to block for them to complete, depending on what your algorithm is. But we have this kernel launch version. One of the things that's slightly counterintuitive if you're used to programming OpenMP is there's fairly high thread overhead in OpenMP, so there are optimal thread numbers. Thread overhead is pretty close to 0 on these things, so launching more threads is almost always the better thing to do.
Are you allowed to have dependencies between threads, like this thread can't operate until that thread's finished?
So remember, the threads within one warp are executing in lockstep.
That's fine, but if you did large, are the warps allowed to have dependencies?
No, the warps can't tell. So you can, you can put barriers in that will block across more threads, but carried dependencies are quite hard. So you need very high levels of local parallelism. That also, the amount of code space you have and the way the registers are used, and that also mitigates against having long-running kernels. So you kind of need small kernels that do very small tasks, and then you relaunch more of them. And one of the things that makes these things hard to program is that's quite an easy thing to do by itself, but you need to leave the memory over there, because you've got, these things are on the other end of the PCI Express bus, which is basically a very expensive piece of string, and so you have to avoid moving the data, which is one of the things that makes them nasty. You do, however, get something through this pane. I apologize for the size of this. This is a piece of official NVIDIA propaganda, and the numbers on here are peak performance. Now, the term that's used in the trade for that is guaranteed not to exceed performance. So whether or not you will ever see either an Intel machine or a graphics card hitting these numbers is exceptionally doubtful. However, by doing this stupidity, so this is last generation, this is what you could buy last year. The peak gigaflops on these things is about half a teraflop per card. And the Kepler, the one you can buy now, is more than a teraflop per card. So, and that's double precision performance. So that is in principle an interesting number. The other piece of good news is, so remember that moving data is really expensive. That's not unique to these things. That's also true on your CPU. And the available bandwidth, so this is, for a CPU, this is the bandwidth from your computer's main memory onto the CPU. And for a GPU, this is the bandwidth from the GPU's main memory into the processing units of the GPU. And that's also a factor of several that you get from doing this. So there are advantages from having these stupid platforms. The downside is they're pretty much unprogrammable. Now, Intel are not sitting back and watching this happen. Intel have something called Mike, which goes public about now. Lots of people have them under NDAs at the moment. This thing is also a plug-in accelerator card. That will change for both GPUs and this thing eventually, but for at least a while now we're going to be stuck with that. What this thing is tens of, they vacillate a bit, maybe 30, maybe 50 Intel cores, which are somewhat more stupid versions of the processor that you're used to. So they're in order. They don't have any of the out of order execution stuff, but they do execute the full Intel instruction set. So life is somewhat better. So Intel are running around saying, don't bother with this NVIDIA thing. It's way too hard. All you're going to do is you can do OpenMP on this, and life's going to be brilliant. Okay, you'll notice they call these things vector Intel architecture cores. That's because each one of these things isn't really a scalar processor. It's a 512-bit vector processor. So you have to do 8 doubles at a time in order to achieve anything like the peak performance on these machines. So actually, this thing is not as different from one of those NVIDIA cards as it looks. In fact, if you do the multiplication now, last year's NVIDIA card had 500 cores, roughly. This thing has 8 times 30 to 50 cores, or vector lanes. So actually, you're talking about the same degree of parallelism, although executed slightly differently. And that is the major pain in the backside with these hardware devices. And in fact, while at a gross level, these things look really different to each other, if we look at what's actually going on, the big change from what we're used to is we were used to one layer of parallelism. We had MPI. MPO is great. And MPI is going nowhere because we still have to communicate between hosts on our clusters. So we're still going to have that. We have a programming model for one layer below that, which is called OpenMP. But OpenMP is a flat memory model programming model. Right? You have to pull an awful lot of tricks in OpenMP to get it to know about things like non-uniform memory access. It's not built into the standard. And a lot of people are spending an awful lot of money at the moment attempting to refactor codes to be 2-layer parallel. The actual cards we have are, so Intel Mic and your conventional CPU are effectively 4 layers of parallel. So you have a host, you have non-uniform memory access regions within the host, you have threads within those non-uniform memory access regions, and then you have AVX vector processing at the bottom. A GPU has 5 for roughly the same reasons. So this is pretty close to unprogrammable, right? Especially because you probably don't get to control the procurement of the machine you work on. Right? Those of us who work for universities tend to use national supercomputing facilities that somebody else procured. Some of the Americans here have already been bitching to me about the fact that the machines they get seem to be determined in Congress rather than on any sort of technical basis. And looking at the Gung Ho project, there's already speculation that by the time we get to 2019, when Gung Ho might go operational, the costs of operating machines will be such that maybe the Met Office won't have one by itself. Maybe it'll share with AWE, maybe it'll share with another meteorological organization. So the odds are that you're going to be programming, whoever you are, without getting to choose which hardware you procure. And remember, these keep changing, and there's a war going on here, and there are new ideas coming up, and AMD have ideas about what happens in this space as well. So do you want to bet your multi-million-dollar programming effort on which one of these is still going to be here in 3 years' time?
So you've said repeatedly that these are unprogrammable, and okay, fair enough. But Rom had a workshop a couple years ago at NCAR where the DG folks showed up and were showing spectacular numbers on GPUs. So can we flip it around and say, you know, what are the examples of folks that have?
So you can do this, and we have hand-coded things onto GPUs as well. It's an awful lot of work for one particular platform.
But they were saying, you know, factors of 10 in 3 days' work.
Actually, you know, I have programmed these, and I am not a good programmer. So I think, but I'm not claiming that I should be the one to figure this out, but I am saying my experience, knowing an MPI level of programming in parallel. I mean, I saw this. I worked it out myself that I had to do something like this, which is what made me start thinking about what could I do to get more. Right? So there was something. It felt like there was something important about someone like me making an attempt to do this and understanding how the algorithm would go onto it. This was sort of the point I was trying to make before, which is that there's something about the way we would learn parallelism and this vector way, right? that I would never have understood if I had to try. You know, and Tim Warburton, I think, Todd, he was the one who, you know, yes, there are like YouTube videos of Tim Warburton, you know, I'm parallelizing on the GPU, and look at it go, right? My DG thing, right? But I'm kind of with you there, Todd. There's some mysterious thing that isn't quite understood.
So the story there is, you can sit down and you can write some CUDA very quickly, and that's absolutely true. High order DG, if it's explicit, is a good example of something which matches really well onto these things. So that's an easier job to do. But if you look at the what goes into actually having model code work, and especially the debugging process on these things is horrible. Debugging even OpenMP is a horrible, horrible thing to do, right? It is much worse on these machines.
Yeah.
And the portability issue of that, right? Even on a conventional CPU, you spend a long time getting that code correct. You will make mistakes every time you port it, and it's infeasible to maintain multiple versions of the code in sync at once with different parallelization strategies and debug them all and understand what's going on. So, I mean, there are people, and
I agree with that, but I'm sort of adding some, you know, the point is that if people who develop algorithms don't feel the pain, so to speak, or there's an idea of how the algorithm can be warped.
So, okay, so the way, we're getting heavily distracted here, but the way that I would put this is, it is infeasible to write code of reasonable complexity in assembler on a CPU. You don't, you write it in C or you write it in Fortran. You do that probably not understanding how a compiler works in any meaningful sense. You do it based on a model of how your processor executes. And as long as your model is sufficiently good, it can be completely wrong because it causes you to produce the right code. Yeah. And so I think it's inevitable that algorithm developers have to have an understanding of how the parallelism works from the sense of having a model. But that model is in terms of how big units of parallelism make sense, what access to memory costs, and those sorts of operations, how synchronization can and doesn't work. Those sorts of operations. I don't think it's productive or useful for that to then mean that you have to write the individual CUDA operations and then port them to AVX and then port them to whatever else, right? So I think you have to have an understanding of how this works. And so I don't believe in automatic parallelization. I think the next slide says that. Okay, so I've just kind of said that one. Oh, I obviously don't have that slide. Okay, so so one answer that gets pushed around every time we have a new option, it happened with MPI as well, and it happened with OpenMP is, don't worry about it, the compiler will do it. No, it won't. And the reason why the compiler won't do it, and I think this is really quite a deep and fundamental reason, is a compiler does two things for you. A compiler analyzes the code that you wrote, and then synthesizes new code in a lower level language. These are the two operations that it does. Of those, the analyze one is the hard bit. Right? Code synthesis, you're right, you can understand how to do it, therefore you can write a piece of software that does it. That's a solvable problem. Writing a piece of software which comprehends what you've written in such a way that it knows which code to synthesize is really, really, really hard. And so the reason why automatic parallelization has really struggled to get anywhere is because if you've written a serial program, then backing out from that where the parallelism is quite hard even from an expert programming perspective, right? It's much easier for you to do that if someone hands you the algorithm than if they hand you the code. So if you now think about what it takes for a computer program to do that automatically, that's a very, very difficult proposition. Fortunately for us, so now that I've spent half my talk time complaining about how hard all this is, we have a really big advantage here. And the really big advantage that we have is that we have lots of obvious parallelism in our algorithms, and the way that we naturally work with our algorithms is in a parallel manner. So this is the finite element version of this. Actually, insert finite whatever you like after in that sentence, because for these purposes, they're all basically the same. What happens is you have a local phase and a global phase. In the local phase, you perform the same small operation locally on a mesh. So if you're a finite element person, that's an element or a facet integral. If you're a finite difference or a finite volume person, then that is a local operation, quite possibly around an edge, possibly around a cell. It doesn't matter. The point is that the way we do it, the way we do numerical analysis is we do it in parallel, right? We derive what happens locally and then we say, and go do that everywhere. So actually for us, thinking in parallel about this hardware is the natural thing to do, which is really good news. And then you do a global phase. Now, the good news about the global phase is that this is a very well abstracted operation. And unfortunately, Paul's not in here because Paul has some exciting things to say about that. So, do I have the?
So by global phase, you mean like some global linear matrix solve or something like that?
Or even just the insertion into that. So even if you're doing explicit, you have a map back to the global vector, right? So you.
Go cell.
We have no global vector and.
So you don't actually store velocity.
So what do you have to define global vector then?
So a state vector. So you do a local operation.
Global model? You mean global model vector or
An array?
or an array per processor?
Right. An array well, but the array per processor is the global vector. The vector may be implemented in a distributed way,
Okay.
but it exists.
Okay.
So the finite volume
So-
analog would be the ghost cell halo update.
Oh.
No, it's not the go cell update. This operation here is just the indirection operation.
So can't you do all the local stuff and then do the halo update?
So you do local here does not mean local to a processor. It means local to a cell.
Basically, it's div on cell.
But so you mean spatial operations?
Absolutely.
Okay, that's what you mean, okay.
Yeah. So you do integral over cell, right? In order to do that integral over cell, what you do is you solve a local problem. You then map the local problem back globally. If you're on a structured mesh, you do that by calculating where to put it back. And if you're on an unstructured mesh, you do it by looking up where to put it back. And if you're in these 2+1 meshes, it's a combination of those two, right? So that's a really well understood problem. And in fact, we understand how to abstract matrix insertion, right? I can describe it to you like that, and I can write a piece of code that does that. And happily, even if you have implicit solves, there are libraries for these platforms that are emerging and getting better, which do that one for you. So Phil Colella has these 7 dwarves, right? The linear algebra dwarves are really well abstracted. What I think is needs to change in order to make this work better, and in order actually to improve our productivity even on a conventional platform, is we need to have equivalently good abstractions for the sparse matrix problem. And I think those are emerging. So I think we have some ideas which I'm about to talk about, but also there are other people doing things which are remarkably similar, and that makes me really happy. Because if I saw us doing stuff at that level and what other people were doing looked completely different, then I'd really question whether or not we were onto the right thing. When I look around and I see a lot of people saying we can talk about the problem in this way, then I start to be a little bit more confident. I'm just going to skip this bit and drop down to here. So this is what I think the exciting story is here, which is to say the solution to the hardware problem, but actually also to the programmability problem, even in serial, is not to program your model. Now, I don't quite mean that. What I mean is actually to program at a layer of abstraction which makes sense for the operation that you're attempting to do, rather than to crash through all the layers of abstraction at once. So we're already used to this, right? You all program to compilers. Now, actually, we have at least one, and the finite element people have 2 useful layers of abstraction above compiler level. So the first one up is the one I was just explaining. I'm going to go into that in a little bit more detail in a minute. This is the PyOP2 layer, and the abstraction here is I do local operations, I do them on a mesh. So the instruction I should give to the computer is, this is how to do a local operation, now go do it on this mesh. Because if I need to then synthesize the code that does the threading or the domain decomposition or the blocking or whatever else you need to do under that layer, because you've given me explicitly the parallelism to use, that's only a synthesis problem. It's not an analysis problem. You've done the analysis for me. Above that, it's even better. So at this level, if you want to assemble, for example, a mass matrix, then the conventional way to do this with quadrature is you locally loop over test functions and trial functions, and you locally loop over quadrature points. You have a triple loop. You write it in this case C. I guess you could use Fortran. They're interchangeable at this level. And you write local operations in here. But actually, in finite element land, if you know which function spaces you're in and you know which operator you're writing, then that was monkey work. Because knowing which function spaces you're in and which operator you've got already told you which lines of code to write here. So you can write a piece of software that writes it. And some very clever people from Scandinavia have already done that. So the Phoenix project says there's a higher layer up here where for a mass matrix, for a Poisson equation, then I've jumped to the traditional finite element equation. I can say, here are my function spaces, which I've defined above, and we'll see how you do that in a second. Here's my operator. So that's clearly the same thing as that. That is clearly the same thing as that. At this level, that's just a symbolic algebra package. You can think of that as Mathematica specialized for PDEs. Nobody's done any computation at that point. It's not really associated with any data. That happens here. So what happens here is it writes that kernel code, it schedules and executes that kernel code, and then it calls the solver, which is the code that you would have written, right? It's just that it can write that for you. And it caches that generation process, because the generation process is kind of expensive. So the first time you run it, you pay a certain amount for the generation process, but then the second time you execute the same thing, which might even be the next time step or the next iteration, you don't pay that again. So for one that's a bit more at home for us, everybody's favorite set of equations, this is the Rabiot-Thomas element. So this is C-grid on triangles. It's an awful element, don't use it, but you know, we can code it really fast. We can do other elements as well. There's your pressure space, it's piecewise constant. I need the test functions and trial functions for that. I produce mass matrices. Those are the actual divergence and pressure gradient operators. I'll show you them in a second. There's a Coriolis operator, there's the skew operator in there. In fact, you can now write that more cutely. You can write skew of u now, because we asked them to put that in over the summer. And you assemble your system, and then I've cut off the solve, but you call solve. And once again, you can see that because we're in this function space, right, so it's just like doing finite volume. You integrate by parts and use Green's theorem to turn your cell integrals into flux integrals. So we just have the jumping the test function multiplied by the normal of the velocity to give you the divergence, and you have a similar operation, which is the transpose of that, which gives you the pressure gradient. And they look like they should do. In fact, cutely, you can tell that that's the adjoint of that. And there's a complete one that's actually got the solve and the time-stepping equation in here. I mostly put this one in here as a small teaser for you for the talk that I'm going to give at the Met Office conference, because one of the things about having a really high-level representation of this is it's an awful lot easier to do manipulations on this than it is to do manipulations on 500,000 lines of Fortran. So that's the adjoint. And to make your life easy, I've highlighted all the changes we made. And that adjoint executes as fast as the forward model. In fact, faster, because it's nonlinear. So we'll come back to that. But that's one of the points here, is that it's easier to work at the right level of abstraction. So if we go back to that chart we had earlier, one of the important things here is to enable people with different skill sets to work on the same code base. Because the historical position we've had is that you need to be your own domain expert, numerical analyst, and computer scientist, because that's all jumbled up together. And if you call the computer scientists in to optimize your code, they walk all over your code, they put a whole load of directives in, they give you back something you can hardly work with. So familiar experience, right? That's also not a win for them because they have to repeat that every time. Whereas in these abstracted systems, that doesn't happen. So let's look at the lower level of abstraction, which is possibly the one that the finite volume people might be more interested in. So at this level, you have, you have kernels, which are these small functions, do one thing at one point on a mesh. And then you have to have a global API, which gives you the ability to glue them together. So the ability to say, do this everywhere. And so the really big change we made this summer was we drank our own Kool-Aid and said, okay, what we were doing previously, which is we're writing the global API in C or Fortran, and then using a compiler front end to attempt to analyze the program to work out how to execute this, is dumb. And the reason it's dumb is because that involves quite a heavy layer of analysis at the high layer, and that's very hard. If instead you take a leaf out of the Phoenix people's book and you write this global API in a nice interpreted language, because remember, all the cost is in here. This is a vanishingly small proportion of your time you spend doing this stuff. And you only do your parallelism at runtime, then there's no analysis, because at the point at which you have to execute a parallel loop, all the information is right in front of you. You don't have to go looking through the whole source code to find it. So that was the big rewrite that happened over this summer, was to do that. So the other people who are out there in this space that I know about immediately, so the current Phoenix system has a sort of more primitive version of what I'm talking about underneath. The ancestor of the system we're working at is something called O+, which does the same thing but was really only targeting a distributed memory, so it didn't actually provide the right information to do this thread synthesis. And that's been in use at Rolls-Royce for about 10 years now. Dune, which is Rob Scheichel's favorite piece of software, also has a kernel type interface. In fact, I know that the Dune people have been in communication with the Phoenix people to get Phoenix to generate kernels for Dune. And there's a thing out of Stanford called List, which also looks really exciting, but for the fact that it's in some really obscure language that I think is really going to affect their take-up. Because does anyone here know Scala? That's right.
What was that?
It's called Scala. But there's an awful lot of this going around, which encourages me. And in fact, I was hoping Paul Fisher was going to be here because I was going to let him jump in at this point and explain the sense in which what he's doing is the same, because he raised this over lunch yesterday. So there's some of Paul Fisher's stuff also operates at that level of abstraction. So that makes me feel kind of happy, because I think there is a natural level there that we might be arriving on.
Now, when I discuss this nice idea with people that are running the machine and doing optimized code, they always say that the interpretation part and all that will kill the performance. Because in a production like that office, for instance, if we take that example, the compile is done once, and then it's executed so many times, so it makes sense.
But as I previously commented, we cache the compilation. So if you run the same problem again, you don't compile again. Where the same problem means the same model settings, not the same data, right? So you don't have to, that doesn't need to necessarily be a problem. There is also, there is a different trade-off here, right? So the level to which you would go up that abstraction tree probably does change depending on who you are, because there are different cost metrics. So if you are the Met Office and you are doing operational forecasting, then wall clock is the only thing you ever care about, and you have relatively massive resources to optimize for one machine to run one execution, and they can do that. That's not how most of science works, right? We're already in a position where if you hire a PhD student to work on a problem your model can't already do, then you'd be pretty optimistic if you think that PhD student is going to produce any physics results. So if you, for the majority of science, we are being killed by the development cost. It's a bit different if you run a national center, but even for national centers, they have some of these issues, right?
Import their code every 6 months to a new NVIDIA chip.
Right, absolutely. So I mean, you can say, okay, the only answer is we're going to write C. If you're going to write C, that is or Fortran, if it makes you happier, that is pretty much the end of doing any sort of numerical work in universities. Because you know, the one postdoc project can't make progress on that basis. So this is this is why I can't full screen on here. Let me move this back over to the right-hand side. So this is just a kind of live demonstration of how this works. And this is the lower level, this is an intermediate level interface because this is kind of new. So this is mixing in the PyOP2 stuff, which is the kernel stuff, with doing Phoenix. So you can actually explicitly see how this stuff works. So what happens is we declare our Phoenix stuff, and this is a really, really simple case. This is the simplest case we could ever think of. This is the finite element identity operator. We're going to solve mass matrix times left-hand side equals right-hand side. And the reason we do that is because that's more than sufficient to break most things. So there's your P1 elements, A grid, for those of you who are of that persuasion. There's your test function and trial functions. There's your mass matrix on the right-hand side and your simplest possible right-hand side vector. You ask it to compile these forms. And in fact, I did. So let me shrink this down. And so one of the things you actually get here is that you get the opportunity. So this is the dumbest way of compiling these forms. So if I just go back up, that was executing that line from the code. So if I now show you what's in mass code, I should print it because you'll see it better. That's a C program which assembles a mass matrix. Now, in contrast to certainly what ICOM does at the moment, all loop bounds are hard-coded. There are no outside lookups. The code is mega specialized to doing this one particular problem. And in fact, this is the dumbest possible version because we're not currently particularly interested in single kernel performance. The Phoenix people can do a lot of low-level optimizations which are particular to a particular form. And so they can do things which on occasions go reduce the number of operations on a complex form by 2 orders of magnitude. Of course, those same optimizations on a different form increase the number of floating point operations on a single form by 2 orders of magnitude. One of the things about doing code synthesis is that you can come up with lots of clever strategies, many of which are very labor intensive and you probably wouldn't bother to do by hand. And you can then either heuristically apply them, or if you're really clever, you can do profile guided optimization to work out which ones to apply in a given circumstance. And that's not because you couldn't do that by hand. It's just that it's too labor intensive. So we get computers to do the stupid work which is too boring or too difficult or takes too long for us to do. And there's a large help about that. But it's even just already a win because you get to generate this from the existing equations. So you get instant code, yeah.
How do these libraries exist optimized for everything that will be shot that could appear on the market? Or?
So well, the point here is that, so Phoenix exists now targeting CPUs. The projects that I work on are producing, we have prototype code which does current GPUs, both the AMD ones and the NVIDIA ones, and we can do OpenCL on CPUs as well to limited extents. There are other vendors out there as well. The point of the exercise is you fix the library once, right? So the whole point of libraries is shared effort. Or code generation systems is the same story, right? So sure, you have to adjust code generation strategies for new hardware, but you don't rewrite every code for that, you rewrite the library. And actually, one of the interesting things about this is as we converge on more stable abstractions, you can rewrite the library, or you can decide that the other guy's library is better and swap out at acceptable cost. So that's already true for linear algebra. So if you are currently using PETC, but you decide that there's a flashy AMG solver in Trilinos that you would really like, the pain involved in refactoring your code to call Trilinos rather than PETC is not very high, because PETC and Trilinos are different implementations of the same abstraction. So the point about abstractions is they enable you to share the load. So sure, you can say, no, I don't believe that, I'm going to do it all myself. And you and everybody else can do it all yourself, and then everybody spends their entire time worrying about low-level code.
How about the manufacturer's library, if they exist?
What manufacturers' libraries, basically. So the manufacturers are jumping on with helping stuff where the abstractions exist. So NVIDIA supports but does not write QSparse, for example. And the reason that works is because QSparse uses the same basic abstractions that every other linear algebra library does. And so vendors can help, but vendors aren't going to solve our problem. They're especially not going to solve our problem when we can't state it clearly. Right? We don't have that level of abstraction, so NVIDIA aren't going to solve that problem for us. If we were in a position where that abstraction was well established, and therefore there was a market for being able to present that level of abstraction well to programmers, yeah, maybe. But we're not there. So NVIDIA are not going to solve that problem for us until we come halfway and can demonstrate to them the problem they want us to solve.
So, David, I really like these abstractions, but I still feel like, as far as what the kind of things that people in this room do, that maybe using these different levels of abstraction to learn what kinds of things the new machines do that the old ones didn't. I mean, because what's going on here is how do we put what we know works well on the old machines onto the new machines without having to understand the details, which, you know, I didn't enjoy figuring out what the warps were, you know, and putting it on there. So I like this, but I feel like we who develop algorithms could do more if we could understand the principles, you know, maybe using these different levels of abstraction to see how to combine maybe different methods. So maybe one doesn't just use, you know, spectra elements by itself anymore. Maybe one uses something else.
So what you're kind of saying is, you're right, is the people in this room are this person.
Yeah.
And so, but that's really helpful, right? This really helps you because it enables you to do this job.
Well,
to a certain
it enables us to do this job how we already know how to do it.
But
No, but
that's not entirely
not really
true. That's not true at all, actually.
Well,
These,
I mean,
these codes are so complicated that if you're a numerical analyst and you have some idea about, I don't know, a new basis function or you know, a new AMR strategy or subcycling strategy, it's really tough to sit around and think, okay, I'm going to now spend the next year developing a code to test out an idea I don't even know will work.
Yes, but I'm saying that I think we are not in a position to yet think of the ideas that can take advantage of this multi-layer parallelism.
Well,
It depends what
And I'm
level of
not,
idea,
I'm not
I guess.
advocating that
Yeah.
we should do pro-be
So it depends which level of
Yeah,
it depends which level of idea you're talking about, because there's also this layer down here, right? So, and at the moment, I think you're conflating those two layers, because at the moment our programming models force us to be both of those people.
Right.
So the computer scientists who I work with who are worrying about things like this diagram here, so this is two-level coloring. So this is a mechanism for doing lots of parallelism in a small amount of memory. So what you do is you carve up one chunk, you hand that to one of these little streaming processors, and then you color that chunk again, and you tell each thread to go do an etch. That's not a numerical analysis optimization, right? That's a straight parallel execution optimization. And the point here is that there is an untapped resource of computer scientists who are actually very good at that optimization, very interested in that optimization, and wish to study that optimization, who know nothing about what the coefficients in there should be, right? So if I was to crudely overgeneralize, the numerical analyst's job is to tell you what that local operation is. The computer scientist's job is to make it happen.
Yes,
And-
but I've had conversations with computer scientists where I say, if I do this problem along characteristics, you know, and it's a straight shot, I can do it at 10 times the speed as how I would do it if I did a normal, you know, continuous Galerkin method. Right, but I don't know that until I talk to the computer science. I mean, I'm not advocating we all talk to them. I just have the experience that I would change how I would do it when I understand from the computer scientists how to do it faster.
So,
But I
right,
don't
so your argument
understand that.
is that if we are omniscient and have all the time in the world, then we get the best, we get the
No,
optimal
no.
solution.
Well, but that's
The-
a question of
No, I'm-
abstraction, like what's
Yes,
what's the
I'm-
correct abstraction?
Yes.
This algorithm or that algorithm? But it may be that some of these ideas are not quite mature for this sort of approach.
Yes, but what I
mean,
see in this sort
but
of
it's sort of
approach
the
is the
target to-
possibility of having a way for us to learn how to deal with the different layers of abstraction that are maybe different than what we've dealt with before. I mean, I see in what David was showing that with the chance of doing that, if only we had examples of how it functioned, that we didn't have to like accidentally stumble upon it, right? Like I did. So I think there's a possibility here for us to learn about what you've done already, for us to learn about how these things interact with each other. You know, there's a middle step missing that's probably not missing for you, but is missing for me.
Yeah, okay, possibly. But
Yeah.
so I mean, where this still comes back to is even if you wish to make an algorithm change, and then ask, for example, what is the implication of this algorithm change across different hardware? That's already massively facilitated by doing this,
Yeah,
right? I mean, the alternative is you go code it 4 times over in the different approaches.
Yeah, I don't
And
wanna
the
do
flip
that.
side, the other way around, right? If you work out, as a guy in Denmark did, a more efficient looping mechanism for going over quadrature, so Kristen Orgod's PhD was on that, then if you have to then do this the conventional way, so the conventional way is to then go to Mark Taylor and say, Mark, I've got a really cool way of you assembling your local elements in your spectral element code. Why don't you recode your model according to me? Because that's what we do at the moment, right? What we do is you come up with ideas, you publish them, you hope that somebody else will re-implement them. That's not what you do in linear algebra. You come up with a flashy new preconditioner, you code it up in the PETSI framework, and then users all over the world flick the switch and get your preconditioner.
Yeah,
And
but
that's-
that's because the abstraction layer has been well worked out for years and years.
Right.
And that's what research is about. So the risk with this is that you fix the abstraction layer and the really big breakthrough, which are actually coming up with the notion of linear algebra in the first place, exaggerate a bit, but it's a bit like that, or new, very different
So,
methods, is, you know, I'm not saying it should fit in there. Well, I'm just saying there's a big difference between working out the right abstractions, and that's really the fundamental work, okay? And then once you have that well sorted out, writing, let's say, I'm being provocative, but any packages with using these concepts, you know, even if you have to pay some programmer to do it really well and really fast in assembly language, you can do that because all this previous work, you capitalize on that, and you can really,
so I
solve the
would,
problem
so
in
I
that
would
sense.
argue that we are now at a point, and I would point to the number of projects that seem to be attacking the same abstraction. We are now at a point where we actually do have a conceptual understanding of where it looks very strongly like a natural abstraction for our sorts of problems lies, which is in this kernels executed over meshes abstraction. And I would argue that we're actually a step on from where you're talking about, right? I think we're at a point where multiple groups, including us, are trying to make that abstraction work, rather than at the point of asking the question of where the abstraction is.
As an intermediate step, can I go into my ocean model and break it into maybe 20 kernels? Right, so basically what you showed before for the round 0 was a kernel.
Yeah.
If I took it and broke it into 20 kernels, would I meet you halfway? I mean, what you're advocating for is for someone to go generate those kernels for me.
I should be really clear here. I fully concede that this higher level of abstraction is special to finite element, right? So there are extra bonuses that you get at the higher level because finite element has such a clean mathematical abstraction. If you are going to do a different methodology for PDEs, and I fully concede that there are lots of reasons to do that, then that level doesn't exist. So I agree. What you're going to do, if you were going to write MPAS in this sort of way, is you're going to write these kernels yourself in C or possibly Fortran.
And that's what we're doing.
Right.
I mean, that's a standard part of the optimization process is to identify kernels,
Right.
isolate them, let someone else hammer on them,
Yeah.
and swap back and
Yeah,
forth.
because you're converging on the same abstraction that we are, right? I mean,
But isn't that a standard way to code optimize? You
So the
you
difference
profile.
is, well, so profile and attack the bits that hurt is slightly different here, right? So there is something different about these kernels, which is, these are specifically kernels which iterate over meshes, which is a bit more special to what we do, right? And it's the natural fallout. So it isn't just finding the 10 lines which are occupying 80% of your time.
Right.
It's a different method from that. And the reason why it's a different method from that is because by attaching it to the relationship with the mesh, then we make explicit the parallelization relationship. Whereas by just picking out a chunk of code which is expensive, then all you have is the C abstraction. All you have is those layers. So that is what makes this kind of different. And actually, even if you're up here, I need to stop because I'm over time, but even if you're up here, one of the things that we would criticize the Phoenix people for is it's quite hard to escape this abstraction. And that's unfortunate because quite often we have the need to insert something remarkably un-PDE-ish in the middle of our model. Even in discontinuous Galerkin space, some of the slope limiters are not really very expressible in this sort of level of abstraction. And so that's why I actually think that this is, even if you're a finite element person, this is an important layer of abstraction, and that you have to expose this layer of abstraction to the programmer, even if you also give them this one.
That's kind of what I meant. That's kind of what I
And
meant.
that's what happens here, right? Because you can do this and make forms that way, and then actually do the execution, which happens a bit further down. But that was just a function that produced a string. I could also say mass code equals string that I wrote. And that's an important abstraction breaking algorithm, which is kind of akin to the fact that you can inline some assembly code in your C if you really, really want to. We tend not to do that anymore, but 20 years ago people were doing an awful lot of it. The compilers caught up. So maybe in 20 years we'll break through that abstraction less here as well. But I think that it would be insufferably arrogant to claim that you had all the solutions and you were therefore going to handcuff the user to the level of abstraction that you were capable of working out. So I should stop because I'm now over time. I should let people go do some work. But I'm happy to answer more questions if you wish to.
That was very
Go.
useful.
So